Hello everyone, my name is Nam Young. The topic today, I'm going to introduce you the GPS system. The outline of my presentation includes the brief history of the GPS and the space segment and the control segment and the user segment of the GPS system. And I also include the basic series of the positioning and the signal processing in the GPS system. For centuries, navigators and the explorers have searched the heavens for systems that the world would enable them to locate their position on a globe with the accuracy necessary to avoid tragedies and to reach their intended destination. On June 26, 1993, however, the answer became as simple as the question. On that date, the U.S. Air Force launched the 24th Navistar satellite into orbit, completing the network of the 24 satellites known as the Global Positioning System. Today, the GPS is saving lives, helping society in countless other ways, and generating 100,000 jobs in the multi-billion-dollar industry. Now I'm going to introduce the space segment of the GPS system. The GPS design originally called for the 24 SVS, at each in 3 circular orbital planes, but this was modified to 6 planes with 4 satellites each. The orbital planes are centered on the Earth, not rotating with respect to the distant stars. The 6 planes have approximately 55 degrees inclination and are separated by 6 degrees right assumption of the ascending node. The orbit arranged so that at least the 6 satellites are always within line of sight from almost everywhere on the Earth's surface. Here, I think I'm going to need to explain what is the inclination and what is the right assumption of the ascending node. The inclination is the angle between the orbit plane and the Earth's equator, and the right assumption of the ascending node is the angle along the equator from the reference point to the orbit's intersection. And on the ground, we have the control segment. There are 5 U.S. Air Force monitoring stations around the globe. They are located at the following 5 positions, and they are tracking the flight information of the satellite and send them to the Air Force Space Command's Master Control Station, which is located at the Colorado Springs. And the Master Control Station contacts each GPS satellite regularly with navigational updates. And these updates synchronizes the atomic clocks on board the satellite to within a few nanoseconds of each other and adjust the ephemeris of each satellite's internal orbital model. The figure above shows that atomic clock that serves as the American times and the frequency standard. And here we come to the user part. We have the user segment. GPS receivers are composed of antenna and the receiver processors and the highly stable clock. The antenna are tuned to the frequencies transmitted by the satellites. And we also have the display part to provide the location and the speed information to the users. A receiver is often described by its number of channels. This signifies how many satellites it can monitor simultaneously. Here is the basic series of the positioning. To calculate the longitude, latitude, and altitude of the target, we need at least 3 functions, which means that we at least should receive the navigation messages from 3 satellites. However, the clock time on the satellite and the clock time on the receiver is not exactly the same, so we need the force function to synchronize them. That means we need the 4 satellite. And as you can see in the 4 functions, the D1, D2, D3, D4, they are not the real distance between the satellite and the receiver. They are calculated by the receiver, but it should be corrected by this 4 item. And the time in the functions are not the absolute time, it's the relative time. And each GPS satellite continuously broadcasts the navigation message at 50 bits per second, giving the time of wake. The messages are sent in frames, each taking 30 seconds to transmit 1,500 bits. The frame is divided into 5 sub-frames. The first sub-frame contains the clock correction data, and the second and the third frames contains the ephemeris data, and the fourth and the fifth frames contains the almanac data. And to broadcast the GPS signal, we first have the navigation message. It has a relatively lower bit rate, and we should encode it with the CA code. The CA code is so-called super random sequence, have a relatively higher bit rate, and can spread the signal spectrum into the frequency domain. And at last, we put it on the carrier and send it out. And at the receiver part, this figure shows that at first we do the demodulation, and by taking advantage of the good autocorrelation property of the CA codes, we can decode the navigation message out. We assign different CA codes to the different satellites, and at the receiver part, we can pass the signals through the matched filter, and we can get the different navigation data out of different satellites and to the different out of different satellites. And here is the little simulation we did, and we use the MATLAB to generate the CA code. Every CA code have 1023 bits, and to see it clearly, we show it by the square waveform. And here, this is the signal spectrum of the GPS signal. As you can see, the GPS system uses the CDMA technology, and it can spread the spectrum into the frequency domain. And that's all. Thank you. Have a good day.